Hi everyone, in this video, we will be talking about straight line, slope, and rate of change. Well, as a motivation, let's say that we are scaling a mountain. Let's call this mountain now linear, okay? And we are scaling this mountain. So this is us, try to go up the mountain. And we will try to study about how steep or what is the slope of this mountain. So let's put in some of the axes and labeling. So I will have the x-axis, we'll have the y-axis. Yeah. So this is the x-axis, this is the y-axis, and let's just represent this mountain using a linear function, something like this. Oh, let me use this tool. There we go. That looks better. And as we climb up this mountain, I will put a couple marks in there. So let's say that when I was able to travel the horizontal distance of 3 units, let's think about it's a mile. Go 3 miles. I go up an elevation of, let's say, 4 miles, I guess. That's a like very small number for a mountain, but you get the idea. So here I will put a flag there, and that is as the location when the horizontal distance is 3 and the vertical distance is 4. Okay, and let's do that again. But let's say 6, 9. When I was able to travel in the horizontal distance 9 units. Let's see where I am. I'm somewhere up here, right? Let's put another flag there, and the vertical distance of that, let's see, 4, 8, 9, 10. Let's say 10. Okay, so this point right here is the point 9, 10. All right, and what does it mean to study the slope of this linear function represent our mountain, Mount Linear? So we see that from the first flag to the second one, we have traveled some distance, some horizontal distance, delta x. And we also travel some vertical distance, delta y. Yeah, so going from this point to the point on top here, we have traveled some delta x and delta y distance. And we can figure out what is delta x and delta y in this case, right? So delta x gonna be 9 minus 3. So it's the difference of this x value and the other x value. So the distance here, that delta x, so we get 6. And delta y is the change in elevation. So that would be the upper y value subtract the lower y value. So that 10 minus 4. And so that also gives us 6. All right, so going from the first flag to the second one, we travel 6 units in the horizontal direction, and we also travel 6 units in the vertical direction. So the slope of this function gonna be calculated as, so slope, we use the letter m, denote the slope, which is the change in the vertical direction divided by the changes in the horizontal direction. So here, if you want to put a formula in this, we can say this is y2 minus y1 divided by x2 minus x1. And so let's say the point x2, y2 is point 9, 10, the upper flags, and the point x1, y1 is the bottom flags, which is the point 3, 4. So then plug these number into the formula, we get y2 minus y1, which is 10 minus 4 divided by 9 minus 3. So we get 6 over 6. And so we get 1. So the slope here is 1. What does it mean? So again, as we have mentioned, the slope represents the rise over run. So rise over run of your function. So starting at a point, the slope telling you what to do to get to the next one. Here it's telling us to rise up 1 unit and over 1 unit to get to the next point. So that's how we compute the slope of a linear function. And the slope here also represents the rate of change. So it also represents the rate of change of the input value and output value. What this means is that when you change 1 unit in the output, in the input direction, in the x direction, when you change 1 unit in that, the slope telling you how much you will have to change in the output direction, the y direction in this case. Okay, so for linear function, the slope is always the same for every single point on that function. Let's say that if I haven't select the point 3, 4 and 9, 10, but using something different, let's say I will keep the point 3, 4, but may pick another point over here. I'm not sure what that is, x3 and y3, and using the 2 new points to compute the slope, I will also get the same result for the slope of this linear function. It's important to realize that the slope of a linear function stay constant no matter where you are on this. Okay, so now let's looking at the representation of a straight line. Two important representation of the straight line is the slope-intercept form and also the point slope form. Slope-intercept form is the more popular one, but in high school you probably have also heard of the point slope form of linear equation. So this is the two way that we can use to represent a linear equation. In the textbook, we also mentioned the standard form, but for the purpose of this course, we are not going to emphasize it at the moment. Just slope-intercept and point slope form of the linear equation. So let's start with slope-intercept. As we know, the slope-intercept form is y equal mx plus b, where m is the slope of your linear equation and b is the y-intercept. The y-intercept is just where your function intersect or touch the y-axis. And that is where the x value of that point is equal to 0. So don't get confused. The y-intercept is where the x value is 0. So the y-intercept here is the point x equals 0, y equal little b. Yeah. All right, so let's look at an example here. I have an equation 2y plus 4 equal to 3x, and we want to write this equation into the slope-intercept form. We see that at the moment it's not in the right form yet. So to write this equation into the slope-intercept form, we're going to want to solve for y in this case. We try to isolating y. So one thing we can do here is subtract 4 on both sides of the equation. So if we do that, we get 2y is equal to 3x minus 4. So I subtracting 4 on both sides of the equation. And to isolating y, something else we have to do is dividing both sides of the equation by 2. So if we do that, we get y is equal to 3 over 2x minus 2. And so this is the slope intercept form of the original equation that were given to us. And we see here the slope of the function is the value m equal 3 over 2. And the y-intercept, of this function is the point where x equals 0 and the y value is -2. That is the y-intercept. And knowing the y-intercept and the slope, we can now draw this function on the xy axis. So I will plot the y-intercept first. X equals 0, y equals -2. So maybe it's somewhere over here. So that the point 0, -2. And again, the slope telling us how much we have to go up and go over from one point on the equation. So here we have the slope is 3 over 2. So it tells us to rise 3 units and to run 2 units. So from the point 0, -2, I'm gonna rise up 3 units. So 1, 2, 3. And I will run. So I just write up 3 units. And I want to run over 2 units because both is positive. So I will write up and go over to the right. If it's negative, then you would go down, but you get the point. So go over 2 units. I got to this point, and the location of that point is, let's see. So we go up 3 units. So the y value is 1, and we go over 2 units from the point 0. So it's 2, 1. And one way to check this is we can plug x equals 2 into our equation, and we should get 1 for the y value, and that indeed the case. So here we have 2 points, and we know that it's enough to draw a linear function using 2 points. So right now I'm just gonna connect the 2 points, and that would be my linear function. Okay. Good. So let's look at let's start looking at the second form of a linear equation. This form we call the point slope form, and it is y minus y1 equal the slope m times x minus x1. And here the point x1, y1 is a point on the linear function. So any point. So for slope intercept, we were really specific about what point we are looking at. We're looking at the y-intercept, but for this form, this point can be any point on the function. Anything that satisfies the function will work. So x1, y1 is a point on the function. And we also note that with this minus sign, y minus y1 and x minus x1, the minus sign is outside of the value of y1 and x1. So that's something that you also have to be careful and keep in mind. Sometimes students would be confused about what is the actual value of y1, whether it's negative or positive. Same thing said for x1 as well. But let's look at let's look at an example here to make the idea concrete. So so here we have an example: y plus 2 equal 1/5 times the quantity x minus 3. And here it's already in the standard form. No, not standard. My bad. At point slope form. But let's try to rewrite this a little bit with the negative sign, so that it look more like the actual form here. So with this, right, I can rewrite this function as y minus -2 equal to 1/5 x minus +3. Why did I do that? Because I want the two negative sign. I want this negative sign and this negative sign, so that it look more like the equation, the form that we have up there. And the more you solve the problem, you probably don't even need to do this anymore. But you can just look at this original equation and know what is the point that we reference here. But for starter, it's always a good practice to rewrite the equation like this with the 2 minus sign. And we know that minus -2 is the same as +2, so we haven't changed anything here. So here we know that this function, so this function has the slope of 1/5. So m equal to 1/5. And this function passes through a point, and this point is the point. So here 3 is my x1 and -2 is my y1. So it passes through the point 3, -2. So it would have made it would have been a mistake if at first we didn't rewrite the equation this way and thought that the point is 3 +2 or something like that. So this would have been an incorrect answer. But 3, -2 is a point on this function. And we can also test it out as well by plugging x equal 3 into the original function and solve for y and see if we get -2 or not. And again, now we have the slope, right? And we also have a point on this graph, so we can graph it. So let's start with the point x equal 3, y equal -2. So 3 is here, -2 over here. So this is the point 3, -2. And this slope of 1/5 here, it's telling us to write up 1 unit. So from the point here, I'm gonna go up 1 unit, and I will go over 5 units. Is that 5? Yep. Okay, so if I do that, if I go up 1 and we go over 5 units, I end up over here. Let's clean this up a little bit. And now, because I have 2 different points, I can connect them. Oops. And that would be the graph of my linear equation on the xy plane. Okay, and what else can we do with this? Another thing we can do with this equation, let me clean this up a little bit, is that we can rewrite this equation using the slope intercept form. So yeah, I'm running out of space here. So let me move this up a little bit, and then maybe minimize this. Resign. There we go. Give myself a little more space. We can rewrite this equation into its slope intercept form. So again, we want to isolating y. Here we can subtract 2 on both sides of the equation to do that. So if we do that, we get that y is equal to 1/5 x minus 3 minus 2. We are not done yet. We don't want x to be like this. We want to expand everything out. So if we expand everything out, we get y equal to 1/5 times x minus 3 over 5 minus 2. What I did here, I distribute the 1/5 into the parentheses. And the last thing we can do is we can combine the two constant, the two value. So when we done that, we get that y is equal to 1/5 x. Here the common denominator is 10, right? So we get minus 13. Oh, sorry. We can use a common denominator of 5. So I probably should review my adding fraction as well alongside with everyone in the class. So we can use the common denominator of 5, and so we get negative 13 over 5. All right, double check whether I did that right or wrong, but let me know if this is not right. So we can see that here again, this is the slope intercept form. Slope intercept, and we see that the slope again is 1/5, and the y-intercept is the point x equals 0, y equal negative 13 over 5, and negative 13 over 5 is approximately no, it's not approximately, but it's exactly negative 2.6, I believe. And so we see that indeed the the y-intercept, the location in which the function touch the y-axis right here, is indeed the point 0, negative 13 over 5. So everything is related. And it's a good practice to go from the point slope form to the slope intercept form. All right, so here let's looking at another example of something that is written in the point slope form. So for the example above here, I have y plus 1 equal 2 times quantity x plus 0. It's kind of funny looking if I write it like this, right? But so we see that if you have not noticed, this is just my silly way to represent the same function as we have looked at earlier. So earlier, for the slope intercept form, oh, sorry, that wasn't the one, but my bad. So I guess I have changed out the example without remember, but so here we can see that if I rewrite this equation, so I rewrite this as y minus negative 1 equal to times x minus negative 0 and 0 are just the same thing, so this is okay. Yeah, let me change the color of this as well. Yeah, minus and plus 0 is just the same thing, so it's all good here. And we can see here that the slope is 2 in this case. And let's pause a moment. If you want, you can pause the video and think what is the y-intercept here. So the y-intercept in this case, it is the point x equals 0 and y equal negative 1. So here, the point that I use is actually the y-intercept because the x value of that point is 0. So in a sense, the slope intercept form is just a special case of the point slope form. And we can also take a moment to draw the graph of this function, but I'll let you do that as an exercise. All right, let's looking at another example here, and feel free to pause and try to work it out before I give you the answer. So here, I would like you to find the equation of the line that passes through the point 2 comma negative 1 and negative 3 comma 4. So I give you 2 points on this linear function, and I want you to come up with the equation. So how can we do this? We know that to come up with the equation, there are 2 ingredients that we need to have. We need to have the slope of this linear equation, and we have to have a point that pass through this linear equation. Well, the second one is kind of given, right? We will have 2 different points that pass through this equation. So either one will work. So for a point that pass through the equation, we are given that. We can just pick either this point 2 comma negative 1 or negative 3 comma 4. Totally fine, but it will take us a little bit of work to get the slope here. So we know that the formula for the slope M is y2 minus y1 divided by x2 minus x1, and let x1 y1 be the first point and x2 y2 be the second point. Okay. So here, plug the value into the formula. Y2 is 4 minus y1 is negative 1. So 4 minus negative 1 divided by x2, which is negative 3, minus x1 is positive 2. So this equal to 4 minus negative 1, so that's positive 5 divided by negative 3 minus 2, so that's negative 5. So we get negative 1 as the slope of this function. And so we have the slope, and we also have a point. I'm going to just use the point x1, y1, 2 comma negative 1 as the point here. So we can put the ingredient together to come up with our equation. So we're going to have to start because this point, the point that we're going to use, the point 2 comma negative 1 that are given to us, is not the y-intercept. So I will have to use the point slope form of this equation. So we have y minus y1 equals the slope times x minus x1. So I'm going to plug in the value of the slope, x1 and y1. And so we get that y minus, so y1 is negative 1 is equal to the slope, which is negative 1 in this case, times x minus x1, which is positive 2 in this case. And so clean it up a little bit, we get that y plus 1 is equal to negative x minus 2. And so this is the point slope form of the linear equation that we are looking for. Point slope. Let's do a little bit of more work to get it into the slope intercept form. So in this case, I want to subtract 1 on both sides of the equation. So we get y is equal to negative x minus 2 minus 1. And then expand this out. I can expand it out and write that y equal to negative x plus 2 minus 1. And so clean this up a little bit. I get that y is equal to negative x plus positive 1. And so this is the slope intercept form of the same linear equation. And the slope intercept form is a bit more useful because we can see the y-intercept here. The y-intercept of this linear function is the point x equals 0, y equal positive 1. And we can double check that if we plug 0 into the point slope formula up here, we will get +1 for the y value as well. And I will also leave you as an exercise to draw the graph of this function. So finally, I will just briefly talk about why linear function are important. Why do we interested in spending a couple of weeks here study linear function? We see that linear function are everywhere. So let's say that if you're driving a car, right, with the constant velocity, it's not realistic. But let's say that you're driving a car with constant velocity, then if you plot the function distance as a function of time, so time here is the x-axis and distance is on the y-axis. If you plot that function, then the function of distance as a function of time will be a linear function, given that the velocity is constant. And what would you get if you measure the slope of this function? Yeah. So let's say that I have some change in the horizontal direction, some delta x, and I measure some changes in the vertical direction in this function here, and I look at the slope, delta y over delta x. What do you think we will get? Well, it turned out that the slope of this linear function is actually the velocity of the car that you were driving, and because you are driving it at a constant speed, the rate of change of distance as a function of time is constant. So it gives you the linear function, and the slope of this linear function is the constant velocity of this car. And as you do the homework, you will see more and more example application of linear function. But on top of that, on top of how useful linear function is, we want to also talk about another more important application of linear function. Let's say that if I don't have a linear function, but I have like some roller coaster equation like this one that I draw, where the function is changing direction, the rate of change changes all the time. Well, in the future, as you take a class in calculus, right now we prepare you to do that, right? As you take the class in calculus, one of the important questions is to study the rate of change of the strength function. It's not linear anymore, so the rate of change is not constant. So for the function, the rate of change is not constant. What I mean by this is that if I zoom in a little bit here and looking at the rate of change at the two locations, some delta y, some delta x, and I'm looking at the rate of change. I'm going to just abuse notation and then just use m here. Let's say m1 is delta y over delta x. Measure some rate of change of the 2 points. That rate of change going to be very different than if you try to find the rate of change at another different location. Let's say over here, where you also have some delta y, let's say delta y2 and delta x2 or something like this, and then you compute the rate of change over here, m2 a delta y2 over delta x2. Clearly we see that in the initial point over there, the rate of change is negative, and then over here positive. So for more complicated function, the rate of change is not constant, but it changes all the time. And in calculus, we have technique to learn more and more. And back to the point, why linear equation is important, because for these functions where we don't have straight line, but we have curve, the idea is that we can zoom into this function, zoom more and more. And even though as a big picture, the equation are curved, but when we zoom close and close and close enough, they look like a straight line. So we can apply what we know about straight line to the curve function. And I hope that was a little motivation for you to study straight line, knowing that it's a foundation of the basics for learning more and more complicated and beautiful equation. And thank you for watching.